Right, hello. In this tutorial, I'm going to show you how to perform a pushover analysis on a 2D frame structure like the one you see on the screen. This tutorial will be based on primer problem 72, which is partially restrained moment frame under gravity and pushover loads. So it's going to be based on this, not identical, but very similar. And the structure, we're going to model it with 4 plastic hinges, moment plastic hinges, that we're going to represent using the new link element in Arena. Right, so we're going to start with a fresh instance of Adina, making sure that we have the Adina structures module and the statics analysis type. We're going to navigate to control, analysis assumptions, kinematics, and we're going to select large displacements and rotations that will capture geometric nonlinearity, or in other words, p delta effects and such likes. We click OK. We go back to control, now to degrees of freedom. We could work with all 6 degrees of freedom and then make sure we have supports to avoid rigid body motions and so on. But what we're going to do is to deactivate set translation, which is the displacements out of the plane of the screen, as well as X and Y rotation. So we're going to operate with in-plane X and Y translation and in-plane rotation only. Okay, so this will be a geometry-based model. So we're going to geometry points define, and we're going to define a series of points for the structure. So we're going to have 0, 0, 100, 0, 180, and 0, 324, and then 360, 324, 360, 180, and 360, and 0. So those are the initial 6 points, and then I'm going to add a few extra points on 10, 180, 10, 324, 350, 180, and 350, 324. So those extra points will allow me to have some short horizontal lines, because I will place my plastic hinges, my link elements at those 4 internal points, right? So let's go to geometry now, lines define, and let's start creating some straight lines from point 1 to point 2, point 2 to point 3, and so on. Add, and then we're going to add the horizontal lines. That is my first floor, and this is my top floor, and save. So that's my geometry. Next, we're going to have some or add some pin supports at the base and some loading. So we're going to navigate to model, boundary conditions, define fixity. Let's add a new fixity called pinned. So we only need to restrain the translational degrees of freedom, and we can see that the degrees of freedom that we switched off at the beginning, they are grayed out, so we don't have to worry about those. And now we have to apply that fixity that we have just defined. So we select our pinned. We could type in here the points numbers that we can identify by plotting the labels, so it could be 1 and 6, or we can double click on that blue field, select the 2 points, right click and finish, and there we have them. Right, so let's now define some loading, and before that we need some time functions and time steps to control the application of the load. So we're going to have 2 time functions, one that will be a constant time function over a time timing of between 0 and 10. So it will span between 0 and 10 with a constant value of 1, and we'll apply this to the gravity loads applied at the connections. And then we need a second time function that spans over the same time and is a ramp between 0 and from 0 to 20. So the factor will go from 0 to 20 and it will be ramped up linearly. And we will use this time function to apply the lateral displacement, this pushover, this push, lateral push in increments. And we also want some time steps. So in how many steps we're going to apply this load, we're going to have 50 steps of magnitude 0.2, total solution time of 10. Right, we are now in a position to start defining the load. So let's go to model, loading, and apply. Let's define a load that we will apply at the first floor. It will be a magnitude of 275. We want it vertically and downward, so it's 0, -1, 0. And then I want a similar load with magnitude 300 that we will apply to the top floor. Right, so we have force 1 and force 2. We're going to apply force 1 to these two points. And we see that they are by default assigned to time function 1, which is constant. That is fine. And we want to do the same with load number 2. Double click on the blue field, select this corner and this corner, right click and finish. Click apply, and we see again that we have time function 1 in here, which is correct. Now we're going to define a displacement, which is going to be a unit displacement of 1 that will be multiplied to the second time function. Translation y and rotation z, we leave them as free. So we save, double click on the blue field, select the top left point, finish, and apply. And now this time function, I don't want it to be 1. I want to ramp up linearly, progressively, incrementally is the word, the lateral displacement here that we're applying to this corner. So we click apply and OK. If we plot the supports, we see that X and Y are fixed and and rotation Z is free. And the loads, we have a maximum prescribed displacement of 20. So it goes from 0 to 20. And a prescribed force that, well, the maximum is 300, which is the one we have applied at the top floor. Right, so we're going to mesh and apply properties to this frame. So first of all, we're going to define a material. So we could go to manage materials or do this directly through elastic isotropic. We're going to add a steel material with a Poisson's ratio, with a Young's modulus of 29,000 and a Poisson's ratio of 0.3. And we're going to define as well some cross sections that we want for columns, for vertical members, and for horizontal beams. So we're going to select a general cross-section type, and here, instead of defining the dimensions of the section, what we do is we type directly the properties. So the cross-sectional area will be 38.5, and we assume, for this example, that the effective shear area in both local S and T directions are the same as the cross-sectional area, and then an area of moment of inertia of 340 and 4020, and a torsion constant of 9.5. Note that when it comes to the section, we have local S and T directions. The R direction is in the longitudinal direction of the beam, and S and T are the two perpendicular ones. And we will see how to control this orientation in a moment. And we're going to add another cross-section, which will be 30 for the cross-section as well as the effective shear areas, and then moments of inertia 139 and 3620 ns torsional constant of 5.28. We can now mesh the frame structure. We need some element groups. We're going to create a beam element group for columns that will have material 1 and cross-section 1. Save that. And we're going to add a second beam element group that is going to be applied to the horizontal members that will have material 1. We only have one material, the steel, and cross-section 2. So all the attributes, all the properties we created, they are showing up on the studio. So we click OK, and now we need to assign those element groups with the properties to the structure, to the geometry. So we go to Meshing, Create Mesh, Line. We're going to start with the vertical members, the columns. We're going to select the 4 vertical lines, right-click, and finish. So those are lines 1, 2, 3, and 4. And here we need to choose a way of orienting those cross-sections. So we can do that through a vector or through an auxiliary point. Primer 72 uses a auxiliary point. Here we're going to use a vector. So both the auxiliary point and the vector, they will allow us to specify how the local S direction of the cross-section is oriented. So if we choose a vector of 1, 0, 0, it means that the local S direction of these members will be parallel to the global X direction in this particular case. So we click Apply, and those are my vertical members. Now we're going to do the same with the horizontal beams. In this case, I want my local S to be aligned with the Y vector, the 0, 1, 0, the Y global axis. And we're going to select our short members first. Right-click and finish, and we're going to apply. And I could have selected also the long members, but I didn't do it because before I apply my mesh here, I'm going to come here to nodal options, and the nodal coincidence check-in, I'm going to set it to no check-in. So this means that when I select and apply the mesh to these 2 lines, if we now choose to display nothing but the mesh, if we look at the node labels, we're going to see that the areas where the long beams connect to the short beams, we have a node duplication. This didn't happen at the short element to beam because we set the nodal coincident check-in to yes, but here we set the nodal coincidence to no. So we have a node duplication. If we select these 2 members, we see that we have node 9 and node 11. Or if we go here, question mark, we have 10 and 12. So we effectively have 2 coincident nodes at these locations, exactly the same location. And this will allow me to introduce some 0 length link elements that will be my moment hinges, my plastic hinges. And for that, we need to have 2 coincident nodes. So this concludes this first part of this model, where we have everything except of the link elements. We're going to show how to add the link elements on the next video, in the next part number 2.